Hello, everyone. My name is Inbal Levi, and today I'm going to talk about exceptions. So let's start. But first of all, I want to introduce myself. So I'm a C++ enthusiast. I'm also an embedded software engineer at SolarEdge, and I'm working on smart home devices. I'm one of the organizers of Core CPP conference and user group, and a member of Workgroup 21. In addition, I'm one of the founders of the Israeli national body, the ISO Israeli national body, and I've studied physics. I also love math, so if anyone wants to talk about math later, you're most welcome. So let's start. I want to start with motivation to this talk. So here you can see two surveys. The left one was made by ISO. The right one was made by me on Twitter. It was a Twitter survey throughout our user group, CoreCP. You might have seen it. And the questions were asking, the ISO one is actually more precise. It was asking how many developers can use error exceptions freely in their project. And you can see that over 54% said that they can't use exceptions freely in their project. And the right one is talking about developers working on embedded systems. And again, you can see similar numbers. So the problem of exceptions handling being projects avoiding exception handling is a very large issue. And I know we're on a virtual setup, but I wonder how many of you would say that you're not using exceptions in your project. I would love to hear your answers later. Okay, so many industries, as I said, don't use exceptions for performance reasons. The error handling mechanism was addressed by a direction group, and this is a special group of people that have been working on C++ for a very long time. It includes Piana and David and Michael Wong and others, and they've addressed the error handling mechanism by contract in 2016 in a way that they addressed that by addressing the predefined conditions. But contracts clearly are not part of our of C++ 20 yet. And they addressed it again in 2018. The exception mechanism was also addressed by Herb Sutter in 2019 by the paper Zero Overhead Deterministic Exceptions Throwing Values. And again, in the recent meeting, the last real-life meeting in Prague, a paper by James Rodwick and others was presented. It's called Low-Cost Deterministic C++ Exceptions for Embedded Systems. And the last two papers I'm going to talk about around the end of my talk, the technical part. I also want to say that I gave this talk in Munich user group, so I think it's very interesting to see it. This topic comes out a lot lately, and I'm sure you're most welcome to see Klaus's talk where he talks about the usage of exceptions. Here, I'm gonna focus on the technical part. So, as I said, I expect a major changes in the mechanism in the near future. So, the talk will go as follows. We're going to start with what are exceptions, very basic syntax. Then we're going to go over history and domain. We're going to look at exceptions overhead in the technical part again. And then we're going to do a design overview and look at some alternatives. And at the end, we're going to talk about what's next in the exceptions mechanism. So, as I said, this is not a talk about best practices of using exceptions, though it does refer very, very briefly to some guidelines. This is not a talk presenting production level code. This is the code appears in the talk is just a POC, and it was ran only on Linux. And concurrency is also outside of the scope for this talk. And it aims to include a historical perspective, but I wasn't there, so everything, all the decision making described is alleged. And hope you enjoy it. So, what are exceptions? Exceptions are a fail handling mechanism. So here we have a function that's called foo, and foo can do stuff. And if in case foo fails, it can throw. It can either throw from, of course, from standard library functionality or other things, and the error is propagated up the stack. So just as I mentioned, we're going to go very briefly of the main guidelines. You can define your exception type. It's recommended to derive from stud exceptions, and it is recommended to throw by value, catch by ref, and rethrow just by using throw and not the value. And this is just general guidelines for optimizing performance in the current exception mechanism. So as I said, this is a fail handling mechanism. And as I've shown before, this is the same foo that you saw in the previous slide. So we could put the try block on the foo and that throws, and then we can have a catch that goes, that tries to catch a specific error type, or we can just have a catch that catch in a general type. And here we can also redelegate the responsibility for the error by using throw. Okay, so this is our main function, and it have the bar function that we saw in the previous slide, and the bar contains the foo. And again, we can catch the error here, but we could also redelegate the responsibility, and that I mean in quantum marks, of course. But in a way, when we decide not to catch the error, we're sort of passing the responsibility to our operation system. So that's a way of looking at the exception mechanism being propagated outside of our program scope. So let's go back a few years. So in the beginning, there were C. Then came C with classes. Actually, then came C++, but actually then came C++ with exceptions, because I'm not sure if you're aware, exception mechanism was something that was considered very early at the beginning of C++, and we're going to see in the following slides, but clearly error handling was a major thing. So let's go back a few years, as I said, see the alternatives that existed. They existed. So we have error codes that basically return value. And this is like the C-style error handling. So we have a function, it does something. If it fails, it can return a value that is not 0. And usually that's that's the common way to do it. And we have a function bar, and it checks the return value from foo, and it can return an error. And here we can do something. This is the way to propagate up to the main. And here we can do something that regards the failure of bar. And another way to approach errors that existed before C++ was using a global. It could be error no for system users. It could be user-defined global, but the principle is the same. You do something, failure inits the global, and the advantage of this method is that you don't really have to manually propagate the error. You could just check the error in whatever scope that interests you. So this is somewhat, I would say, in some ways it could have been considered better. In some ways it's not. Clearly globals have their own issues, but just notice this. This is an interesting difference. And okay, and I just wanted also to mention that. Okay, wait, let's see. Sorry. All right. So I just wanted to mention that this is the common practice also nowadays, not for C code. So let's continue. So why exceptions? Exceptions make it easier to adhere to the best practices. They give error handling a more regular style. Makes error handling code more readable, and it makes error handling code more amenable to tools. So this is actually a quote from the first paper that suggested exceptions to C++ standard. And the design of the mechanism of exceptions took approximately 5 years. It finished in 1988, as I said, very early. Okay, so let's. This is a quote from Design and Evolution. So, in the original design of C++, exceptions were considered but postponed because there wasn't enough time to do a thorough job of exploring the design and implementation issues, and because of fears of the complexity they might add to an implementation. In particular, it was understood that poor design could cause runtime overhead and significant increase in porting times. So, as I said, exceptions were considered very early, and you can see here some responses to the original exception mechanism to the paper that we saw before. And you can see the responses were from a wide spectrum of companies. You can see here Microsoft and Ericsson and Apple, IBM, others as well that Biana approached to. And again, this was something that was debated very broadly. And I'll just mention here that some voices have claimed that exception may lead to bad quality program in a very early stage of this design. And we'll go back to that later and think, where did it came from? But nevertheless, exception mechanism was accepted to the first standard of C++. And here you can see the section regards that. So the following assumptions were made regarding exception usage in this early design. And this is again from the paper of defining the design of exceptions. So exceptions are used primarily for error handling. Exception handlers are rare compared to function definitions. Exceptions occur infrequently compared to function calls, and exceptions are language level concept. So we're going to go over those assumptions and see how do they fit to the current version of exceptions that we have today. So original design, exceptions are used primarily for error handling. So it's true that control flow management is discouraged by the formal standard publications, and the existing practice really rarely use exceptions for control flow management. But do notice that C++ does not return to the throwing code. So it's a design decision that were made again very early. It goes back to the catch block. Exception handlers are rare compared to function definition, so it's true that the formal usage recommendation say that exceptions are costly, and clearly you don't want to use them in a time-sensitive, in real-time code. If thrown, we have reached to a point where cost is the least of our problems. So they are used in code bases that are not sensitive to that. Exceptions occur infrequently compared to function calls. That's also true. Standard library does use exceptions extensively. So, and this is one of the main issues that we have today. And it is common, though it's common to use alternative error handling because of this, and also to avoid using the standard library. And exceptions are language level concept. That's true. They are platform independent, and the ABI is defined to C++, but the general concept is really something across different development languages. I also want to mention that other languages do have best practices of managing control flow for the exception mechanism. I had a talk about it yesterday with some very nice people. So, um, exception overhead. So the main difference between C and C++ is the cleanup process is now part of the language in constructors and destructors, clearly. So but by using set jump and long jump, we break the contract between the user and the language. So clearly we can't use set jump and long jump just like in C++. I will also just mention two more terms. A happy path is the default scenario with no exceptions thrown, and a sad path is the path which includes error. And I just want to mention here as well that MSVC supports different behavior for the jump functions, but we're not going to focus here in this talk. We're going to focus on GCC particularly, but there are other things exist as well. So just a few words about Happy Path. And this slide I've added after giving this talk, again, as I said, in a Munich user group, because I had a question about it. So I don't want to focus on, in this talk, I don't want to focus on comparing Happy Path to Sad Path. It's clear, we will see a short benchmark later, but it's clear that it's costly. But I just wanna point out the overhead that we do get on the Happy Path. So for return values, of course, we have the fact that the error is occupying the return value. So now we can't use it freely, and it adds the need to manually propagate the error, as we saw before, and it adds an if statement which eventually translates into instructions. By using globals, clearly, as I said, the multi-threading is outside of the scope for this talk, but clearly it adds it's a problem in a multi-threaded environment, and it's limited. You have to manage the global in a way. And exceptions have other overhead that is for the Happy Path. So first of all, when you do compile with exceptions, you need RTTI information. And there's also catch tables created, and additional assembly that is called the landing pod and is actually created in a different location than the regular control flow to have, in order to avoid getting cold code into our RAM. So basically, there's the hat path and the hat code that is on the cache, and if there's exception, then we'll jump to a cold code. And of course, there's the runtime overhead that just loading cold code from memory in case they are thrown. But again, this is just to understand what happens there. So let's go deeper into the sad path. So now we're focusing on the sad path of the case of throwing errors. For exceptions, of course, sorry. And I've compared the throwing mechanism to return code value. And just to make sure that we are on the same page, I'm using here a throw by value, catch by reference, of course. So this is the mini benchmark, and you can see here that exceptions are 435 times slower than the return value. And the size, I've tested this on x86 and on ARM, and the size is more noticeably larger here on ARM. But yeah, you can see that there is overhead. Again, this is the setback. And there's a clear observation of the overhead, sorry. And as I said, they perform worse on ARM. So two main implementations for exceptions exist. The first one is table-based, which is what GCC and Clang are using, and it's better for happy path results. And the second one is frame-based, which is also called code approach. Sorry. And MSVC uses that, but this is better for sad path results. I have focused on GCC both because this is a platform I'm mainly working with, but also, on Linux and GCC, but also because I think it makes more sense. The assumption for optimizing better happy path makes more sense to me. So table-based implementation, as I said, have some overhead in the program. I've mentioned it before, but this is now referring to the case that we're using, the set path. So again, RTTI will be generated, and this is for both cases, of course. Exception handlers will be defined, and each catching function will contain additional information of the catchable objects. And this time, we're actually going to use this code when throwing. So the functionality is basically implemented in two main libraries. Again, on GCC. So we have libgcc, which contains the functionality of stack unwinding and frame management, and we have libstud C++, contains the functionality of exception handling. This one is aligned to Itanium CXX, and there's also a Itanium document regarding this functionality, but it is language independent. And here I've added just the list of the functions that are part of the handling the exception mechanism, so that you can you don't have to read all the names, but you can definitely see that there's a lot of them. By the way, I haven't mentioned that I'll take questions at the end, because this is quite a long talk. I'll be happy to be at the table and get your questions later. So the stages of exception raising process. So first of all, we allocate the exception. And this is a call for allocate exception function. Then we throw. That means that there's a call to throw, and the lookup phase starts. And then in case there's some catch statement that deals with this type of an error, then we can also get to the cleanup phase. And I'll explain again a bit later. Just notice that in case of a failure, there's an emergency space located, and you could and the exception will be allocated only in certain conditions. So, for example, it could be only under 1 kilobyte. It can only have up to 4 exceptions in a single thread, and other conditions that relates to multi-threaded environment. As I said, I'm not going to go deeper into that. So this is just in case that we failed in allocating the exception. Exception in general can be allocated in whatever size that we want. So let's go deeper into those phases that I've mentioned. So the lookup phase triggers start unwinding call for this function called raise exception, and it passes the flag search phase. So we're going over the stack, and we're basically looking for a function that catch the type of an error that we've thrown. And in case of a failure, there's instant call for terminate, for stud terminate. Clearly, there's no cleaning of resources. And in case of success, we return handler found. In that point, we're going back down the stack, and then we start the cleanup phase, which triggers the same function with a different flag called cleanup phase. So, okay, so the cleaning process is as follows. The personality routine, cleaning the stack frame, takes over. So basically, we have reached to a certain stack frame, and we're cleaning it. Then we continue by calling unwind resume. When we reach to a stack frame that actually contains the catch statement, suits the certain type, then we call begin catch and end catch. Begin catch basically treats the exception, modify relevant data. It's sort of global data that counts the number of exceptions that are currently active, and it decreases the number of exceptions. And then it can end catch can call to terminate or rethrow according to success or failure of the process. If, for example, we needed to do something in the catch and we failed, then we'll terminate. And if rethrow is called, then we just continue unwinding the stack. So To go over this process with drawings and to make everything a bit more clear, let's do that overview. So the complete progress is as follow. We have a subroutine, and this is the nested subroutine on top, and the one on top that we just saw before. For in this example, it could be the bar, foo, and main. So first we allocate the exception. Then, in case of a failure, in case we couldn't allocate, then we just call stood terminate. In case of success, we throw, which means we start the lookup phase, and the lookup phase goes by the up the stack and looking for our appropriate function. And in case of a failure, again, we terminate. In case of success, we start the cleanup phase. So we go back down and we start the cleanup phase, and we do the stack unwinding. We look for the proper catch, and we call the cleanup methods for each stack frame that we are closing. And in case we found a catch, then we transform here, and then we resume execution on the catch frame. And if a finally block exists, we also execute it, and then we resume in the catch block. So let's have another design overview, but this time let's look at the details of what are the things that we've defined that we want in the exception mechanism. So these are the assumptions from the original design of from embedded perspective of the exception mechanism. So we want a type safe transmission, and that's clear. We want no added cost unless we throw an exception. That's close to what we have today if you put aside the size and the RTTI generation. Handlers can be written to catch a group of exceptions. So again, I'm coming from the embedded world, and I'm looking for assumptions that could be costly. So I think this one might. We want to allow cooperation with other languages, especially with C. That actually makes sense, and I wouldn't think that we should avoid that. But that's something that is part of our mechanism. Exception occur infrequently compared to function calls, so that's also great. And I'll show later that the majority of the community is also, going forward having even less exceptions. Type-safe transmission of arbitrary and narrative information. So when I look at this demand, I thought that this might be a bit a lot to ask. So we could also consider a design that doesn't have this requirement. And exceptions are primarily for error handling and not code management. So again, these are the assumptions. I would think that this is a good assumption, but actually I had some talks during this conference with people, and they convinced me that this could be considered. So again, I'm not suggesting a specific thing here. I'm just saying that we should really look into those assumptions and reconsider them maybe. So okay. So let's take a step back and see how the exception mechanism is relating to our general system. So there's a subroutine, and again, as I said, there's a subroutine on top of it and the program. And again, if we're an embedded system, occasionally we have an OS, operation system, and of course there's the platform. But I think some things have changed since we first described the error handling mechanism. So even if I do address embedded systems, a lot of embedded systems today do have some connection to the cloud, to the web. And in addition, they usually, again, this is very dependent, and embedded is a very broad spectrum. But occasionally they do have the ability to run more than one program on the platform. And of course, it could have been that on the site, there's additional platforms that are coupled in a way with the platform, either for reasons of to avoid crashing or other things, but there could be the more than one in the site. So I want to have another quote from Design and Evolution. I think it's a very interesting one because it really summarizes what I feel about exception handling mechanism and error handling in general. So no single unit of a system can recover from every error that might have happened to it, and every bit of violence that might have done to it from the outside. In extreme cases, power will fail or memory location will change its value for no apparent reason. So we really, I think this quote really puts the spot on the fact that we're addressing error handling as part of a bigger system. So there are roughly three and a half types of errors. And I mentioned before that the whole community is moving toward having less errors, less exceptions in the code. So the first type of an error is a program bug, which might resemble for today's exception as a logic error. The second one is a recoverable error. And the third one is a terminal error. So things like overflow, etc. Uh, these contain errors which invalidate the program, for example, stack corruption, and errors which exhaust resources. Both of them are types of errors that we can't come back from. So, as I said, it's in recent years it's have been suggested to decrease the number of exceptions that we throw in our program, and basically to just focus of throwing the third type of error, because the program bugs are things that we would like to identify in the early stage of development and before the code moves to production. And the second ones are things that I mean, we don't want to do too much of a logic to handle with those with errors, or at least that's the design that I see in front of me. And the third one is the one that's really suggests throwing exceptions. So this was the design section. Now we're going to move to alternatives. So some techniques for exception mechanism can certain techniques can be used to improve your exception mechanism in case you're working on embedded software. And I think first of all, I want to disclaimer. I want to say that not all of those techniques are suitable for every project, for every company. Uh, it depends on the trade-offs that you're willing to do, but these are things that you could maybe consider. So first of all, you could use the current mechanism and library facilities to optimize. So as we saw before, the RTTI information is generated, and it could be that if we move to just a single type of exception, we might reduce the amount of RTTI. The second thing we can do is override function calls to libstd C++. Now, again, this is a POC. This is not how we'll do it in a production code, but this is just the general notion of doing the work ourselves. The third thing, we could basically re-implement parts of libstd C++ and compile, add it to our project. And four, we could use some alternative mechanism. For example, MSVC have the structured exception handling mechanism that is not by C++ standard exception handling mechanism, though it is used to implement the second. But again, we could have considered, if we were on a Windows platform, if we were using MSVC, in general, we could decide that we want to change from C++ standard to different implementations. So I've tried 1 and 2 just to see the effect and measure, because I always love to see how things that are how things are in real life and not just in theory. So let's look at the previous case. So I moved from throwing a few types of exception to a single type, as I said before, aiming to minimize the RTTI information. And so here we can see our single type throwing exception versus a return code. So first of all, you can see that the ratio is much bigger because this emphasizes that just by adding exceptions to our code, we have the overhead as suggested before of RII, and the fact that this ratio is bigger says that it just emphasizes that the addition alone, it doesn't matter how many types of errors do we add, creates the overhead. Sorry. And you can see on ARM similar ratio, though smaller. And just to compare between throwing 3 types and throwing 1 type, so here I compare them, and I got some gain on runtime, mostly on ARM, but not something that is very significant, at least in my opinion. Again, this is benchmarking on not on real life code, but on my tests and experiments. And you are most welcome to go and try and see how these things act in your code. I will say that there are, again, I wasn't aiming for a full benchmark, but there are 2 very interesting papers by Ben Craig, is also in the committee of C++. He benchmarked both the size and the size overhead and the runtime overhead for different platforms, and I linked to them at the end. So you're also very welcome to go and check those. So then I've moved to the second option, and I've tried to re-implement the behavior of the exception. So let's go over this code. So this is really, again, this is just a POC. And here we can see our main function. And this function calls some function that throws. Now, the throwing function is defined here, and it throws an exception. And it includes, this is the definition of the exception, and it includes the library. And the library, what it does is basically re-implements the allocate exception and the throw. So what I did here is it re-implemented allocate exception by returning some kind of a global buffer, which is addresses the dynamic allocation overhead. And the second thing I did was, and again, this is not a real solution, it's just a POC to see our abilities. So I just terminated, or basically I exited properly when instead of propagating up the stack. So this is really, this code really does nothing. But you can see that here you can see the size of the buffer that I returned, and the call for the call for constructing the exception, and we just exit. So this thin implementation that I've just showed, you can see here that it have a ratio that is very similar to the ratio of return code versus throw. So this is the thinnest throw that you just saw. This is throwing 1 type of exception. And you can see, just for comparison, this is how comparing throwing or 3 values to return value. So you can see these are very similar numbers. So that means that if we move from throw to thinner throw, or re-implementing these parts, we could actually achieve something that is very similar in behavior to a runtime. Of course, the size is still big because we still need to save the tables, the stuck and winding tables, etc., and the handlers of the exceptions. But I still think it's very interesting findings. Okay, so I want to show here what I think that could have been some kind of ideal throw mechanism that I would have liked to have in the following years in the language, in C++. So you can see here a function, And in case the function fails, it can throw. But I would love to have some way to customize this throw and decide whether I want to unwind or whether I want to allocate. I think other people have also mentioned similar ideas, but I think it's really important to identify um, that we're making decisions here that aren't necessarily suitable for all platforms. And here what I'm doing is basically the subroutine is telling the program how it wants to act in case of a throw. There's another way to do it, and this is by just another design concept to do it. It's not a technical way. Is just so we could define in the beginning of the program or in the executable the way that we want to address throw. In this way, the program can actually sort of impose the way that it acts on all the subroutines of the program. So let's look at the alternatives that I mentioned in the beginning, the papers by Herb and Low Cost. And I want to show you the technical details of those papers. So Herb's, as I said, the zero overhead deterministic exception throwing values paper is doing those design, having those design decisions. The first one is first of all, it mentions it identifies that the dynamic exception mechanism is have a large overhead, and program bugs shouldn't be addressed by exceptions. So, as I mentioned before, the general direction of this paper is to first of all um, educate the community to use exception mechanism only for the purpose that we've seen actually in the original design for identifying exceptions. And as I mentioned before, decrease the number of exceptions in our code and avoid using them for things that aren't necessarily suitable for exceptions. And also, he addresses the fact that allocation failure is not a regular exception, because allocation failure, as I mentioned before, is something that the program could not come back from in a way. So again, he says that we should define errors only as recoverable errors that we can address later, and replace those errors with things like status codes, stood expected, and I will mention it a bit in soon, and deprecate, basically suggests deprecate logic error from the reason that I've mentioned before. Logic error is something that we need to address in the development of the progress and not later. So the technical part of what he does is basically he's using a statically typed error so that we'll avoid the RTTI overhead. He also addresses the size of the code, size of the error, and he returns it on the stack, so it's not dynamic allocation anymore. And the third thing he does is basically suggests returning something that is union style from the program. The union thing can hold both success or an error, and a boolean that basically tells us which one is it. And this mechanism is not it's not the classic return value mechanism that we're familiar with, because it contains more, as you can see, but it somewhat uses the same principles in the fact that the stack is the thing that holds the error back. But I just want to emphasize here that it doesn't mean that the developer will implement this union by himself. This is something the compiler would do behind the stage. And as I said, stood allocator, it can, can be predefined to define sort of the whole program, the behavior for all the program. So this is something that what I addressed in the previous slide, um, but just in a one direction. So the program defines the mechanism for the subroutines, and in general, it allows the programmer decide which error mechanism he wants. So the second paper that I've mentioned is low-cost deterministic C++ exceptions, and the proposal focuses on minimizing the cost. Again, in technical perspective, so first of all, it reduces the data needed for stack unwinding. It replaces allocated exception with values returned on the stack. Again, they're defined differently, of course, than what we have today. And they're using global to rethrow, because the rethrow mechanism is also quite complex. I haven't got into that here. But when rethrowing, we have to sort of change our context switch, do some progress, and then go back and rethrow. So these both proposals are, I think, they're very interesting. I think as I said, they're addressing the problems that we have today for the exception mechanism, and I believe that they're gonna have a major influence on the way that the exception mechanism exists today. So to conclude, I want to say that you can create your own alternative. So if, in case you're on an embedded performance, um, an embedded system that needs high performance, you could do all sort of design decisions that are similar to the POC that I've just shown. Of course, with the trade-offs needed, the fact that developing this mechanism will cost developers time, etc. But you could decide that this is something that is important to you, and in this case, you can decide avoid stack unwinding and replace with all sort of alternatives. For example, you can signal to a different process. Sorry, you could report to the cloud and send something, and then crash. For example, I'm familiar with Watchdog. It could be a design that includes Watchdog that restarts your program. So you could decide that you just want to crash, and then the Watchdog will restart your program. You could use some kind of pre-allocated space, as I've shown, and you could uh, try to do other things like just minimizing the amount of the different types of exceptions in your code. I believe it could cause reduction in overhead. So other suggestions for error handling in general exists. So as I mentioned at the beginning, contracts are something that addresses predefined conditions, that uses predefined conditions to solve to avoid errors in the early stage before they happen. And another interesting proposal is stood expected, which basically passes the value that is expected. In case this is not what we get from our function, then there's a callback, or we can do additional things to address that. And just another interesting thing that I think it's worth mentioning is that Bankreg is collecting data for generally data regarding the exception mechanism, things that I've just shown, and the general known common knowledge. So this paper doesn't exist yet, but it will in the future, I'm sure. And there are also other holistic approaches in the committee. For example, there is a paper by Bloomberg, by John Lacus and Westlove, defensive checking versus input validations. And I think this is a very interesting paper. I've had a chance to review it in a somewhat late stage, but I think it's a very interesting paper. It tries to identify the difference between errors that we get on production and errors that we get on development. And there's another interesting notion by Stefan and Derek, suggests that they're considering sort of adding flexibility uh, to how do we define what is an error, and they're suggesting to propagate the error up and let the caller have some decisions regarding that. And I've also talked with Lisa, and she also have her own perspective on that. So there are really different people in the community that addresses that, and I'm sure we're going to see some progress in the near future. So as I said, we need to separate the semantics from the implementation. So uh, exceptions are a semantical definition, or they're programming paradigm, but development paradigm, but they're not necessarily coupled with the current implementation that we have today. And we also need to allow behavior suitable for performance sensitive applications. And I would think that adding some customization to our current mechanism would be the right direction. And as I said, the overhead already exists. So just adding the customization is something that we can only gain from. So in the last year, the keynote was by the previous year for CppCon. The keynote was by Biana Sturpstrup about C++ 2030. So a lot have happened in computing in the last 30 years. And as I mentioned, over 50% of embedded or real-time performance sensitive systems can't use exceptions. So I'm suggesting let's reconsider our environment, reconsider the decisions that were made, because today's embedded systems are not the same thing that was 30 years ago. And we really want to consider the big picture. And I've added here, as you can see, a developer that is crust, because I wanted to add here that today our error collection is also done differently, and it is rare that on production code on the systems, developer would go and check the errors by himself. It usually be collected to a log or to the cloud. So I think that's also something that we want to consider, the change of a paradigm. And I think today the lack of observer for those systems is something that is new. And I invite you all to share your ideal exception usage by emailing me. I invite you to experiment with the exception mechanism and suggest alternatives. As I mentioned, I think major changes will be made, and I would really love to see what do people that are part of the embedded community or others feel that is necessary in the embedded in the exceptions mechanism that they want to be able to use. And to conclude, exceptions, as I said, were designed around 30 years ago. And I really think that we should reconsider the design decisions and let's rebase this mechanism. So those are the links that I've mentioned before. As you can see, there's a lot of them. I've collected here some historical references. The technical references that I've mentioned are very interesting. Feel free to go and research every one of them. There's two talks that address the unwinding mechanism that I haven't got deeper into here today, because it's also it's a complex mechanism, and I couldn't have put that in an hour. But there also the fact that people have done it before, and I would prefer not to repeat them. So this is a talk talking about unwinding in Windows, and this is unwinding by lib the similar way that Clang is doing. And there's a lot of other interesting references here. You're most welcome also to look at the benchmarking that I've mentioned, and I would love to get your inputs. So I hope you're now inspired to go and explore your systems error handling and reconsider them. And feel free to email me. I would love to hear your opinions about it. Thank you.